Okay, so today we are going to talk about nonlinear gravity. So far we discussed just the linearized theory of gravity and its predictions. So we learned that spin zero gravity does not work experimentally. It is ruled out already at the linearized level, and then we moved to the second alternative, which was the spin 2 gravity, and at least at the linearized level we said that it works. Well, we worked out some of its predictions, and now we know that they all those linearized predictions agree with experiment. So it's a phenomenologically viable theory, at least at the linearized level. So then we should ask what would be the full theory beyond the linear order. So to discuss that, it would be good to first go back to the case of a scalar gravity and see how would we answer that question in this case. So at the linearized level, what we put here was some t0 mu mu, where this index 0 here would have the meaning that it's evaluated at zeroth order in the phi field. So if we have the full action, then in the full action there is some matter fields and there will be the phi field. They will we are going to couple them together, but this t0 was evaluated by setting phi to 0 everywhere in the action. And of course that is a reasonable thing to do if we are only discussing weak fields and linearizing phi. Now imagine we want to ask what would be the full nonlinear theory. For instance, the systems, we know that the gravitational field of the system carries also some energy. For instance, we have bound systems, gravitational bound systems, in which there is a gravitational potential energy which is negative. That's why they are bound. Or, for instance, we discussed dilaton waves, a new feature of the relativistic theory, which did not exist in the Newtonian gravity. And we saw that these dilaton waves, they carry energy and momentum. Therefore, we should ask, in general, how would that new source of energy that so far we ignored, how would that gravitate? Which means that we should ask how to generalize this equation to higher orders in phi, to include the mass or energy of the phi field itself. And so what is the answer to this question? The answer is actually not unique in the case of a scalar gravity. So just from the theoretical point of view, we could do various things here, and they would all be correct. There is no principle that fixes this. Of course, if scalar gravity was the description of the universe, then we had to go and check with the in actual systems, go and check more carefully to determine what would be the correct generalization to nonlinear level. but at least from a theoretical point of view, there was no unique case. For instance, we could postulate that this is the full story at the full nonlinear order, meaning that we just plug in here the part of the stress energy tensor which corresponds to matter field by setting phi to 0. This equation would make sense. Whether it would describe the universe, that would be a different story. Okay, now, so of course now this theory is ruled out even at linearized level, so there is no discussion of doing that. There is no reason to pursue this. But then if we go to the case of a spin 2 gravity, then we had some more complicated tensorial equation that I'm just giving it a name. Now we can ask, and here we decided that we should put the stress energy tensor again at zeroth order in H. Again, we should ask the same question. Now we want to include the energy which is included in the gravitational interaction or inside the gravitational wave. So what do we do? Here the answer is actually more or less unique. There is no freedom for instance, I cannot postulate that this is a full equation. And what is the reason? The reason is that the left-hand side of this equation, as we saw before, is identically conserved. So if I act by a derivative d mu on the left-hand side, that is just equal to 0 as an identity, regardless of what is the solution for H alpha beta. Which implies that whatever I put on the right hand side has to be also conserved on the equations of motion. But of course, the zeroth order stress energy tensor is not conserved exactly, because for instance, we saw that if you have a binary system that is moving, it emits gravitational waves. So it loses energy into gravitational waves. What that means is that the energy and momentum inside just matter field won't be conserved. We have to add extra terms to the right hand side if we want it to be conserved. So there are various corrections to the right hand side of this equation that one needs to add. We can try to organize them as an expansion in this gravitational field H mu nu. So for instance, this T mu nu 1 is first order in H mu nu, and it corresponds to, takes into account some of the gravitational interaction between matter and H mu nu field. And then we should continue. Plus, we also had the gravitational waves, which themselves had some energy momentum tensor that we showed by little t mu nu. And that started from second order in H mu nu. So if we remember, we said that we write some action for H mu nu. So we have some gravitational action. How did it look like? It had the following structure. There was a kappa. How did it look? Something like kappa over 2 d4x, maybe a minus sign, and then we had d mu h alpha beta d mu h alpha beta plus some other terms. Then we also had the coupling to matter, 1/2 d4x h mu nu t mu nu as zeroth order, and then there was also the matter action, which I collectively show them by psi. Okay, so now let's look at this action. Let's see what's happening here. So we want to put something on the right hand side of this equation to be so that it is conserved. And so let's consider some simpler examples. Suppose there are two fields, psi and chi. And we write some action for psi and chi. Say these are two scalar, free massive scalar fields. So we have d4x and then minus 1/2 d psi squared plus m squared psi squared. And then we have d chi squared plus m2 squared chi squared. So if I have a theory like that, we have these two fields, psi and chi, which are decoupled from each other. There is no interaction between psi and chi. I could even imagine adding interactions between the psi field itself. But suppose the psi field and chi field are decoupled, there is no interaction between them. So this action is psi and chi can be written as some action for psi plus another action for chi. The moment you have a situation like that, then we can use the Noether theorem. We can use it separately for these two actions and derive two conserved energy momentum tensor. So we can derive T1 and T2, or T psi mu nu and T chi mu nu. Two energy momentum tensors which are separately conserved. So d mu of this is equal to 0, and also d mu of which is not surprising. If we have systems which are decoupled from each other, they separately conserve energy and momentum. If we introduce coupling between the two systems, on the other hand, then they can exchange energy. And if that happens, so if I introduce a coupling, some coupling between psi and chi, the moment I introduce this coupling, then the two systems can exchange energy and momentum. And then there is we no longer have two separately conserved energy momentum tensors. There will be only one total energy momentum tensor that is conserved for the full system. And that is the object that we derive from by applying the Noether theorem to the full theory. But there is no way of applying Noether's theorem only to part of this system. There is exactly because this term exists in the action. Then we won't have these two conserved ones, but we will have only one total T mu nu which is conserved. Okay, now let's look back here. Here what we called T0 was the stress energy tensor that we derived from the matter action by ignoring gravitational interactions. So we are considering a similar situation. We have separated the action into various parts and we derive T mu nu from one part. This T mu nu is conserved as long as I can neglect the interactions between the two sectors. The moment I want to take into account those interactions, then this T0 will not be conserved. There will be a total T mu nu that is conserved, which has to know about the full action, not just one of them. Okay, so how would that look like? There will be a T mu nu coming from this part of the action, the quadratic part that I wrote for H mu nu, and this is what I called T mu nu 2. This is the part that tell us about the energy and momentum in gravitational waves. So if I have a system that emits gravitational waves, far away when there is no matter field, we still have some energy and momentum carried just in the waves, and that is in here. If you remember, it has some expression which was quadratic in H. It was something like something proportional to H plus dot squared plus H cross dot squared with some proportionality constant. So that was this term. And then there will also be a contribution because now there is also this interaction term between the two. That corresponds to the energy, to the corrections to the energy of the system when there are actually both matter fields and gravitational fields. They are coexisting. Like for instance, where the actual system is. So there will also be a contribution from this, and that's what I call T mu 1. So as you see, if I want to derive some conserved, if I apply nodal theorem to this part of the action, it will be linear in H mu nu. So that is why I call it T bar mu nu. Now, what is the meaning of these dots that I'm putting here? You might ask, isn't it the full story? And the answer is no, it's not the full story. Because, of course, we want this equation to be the equation of motion for this H mu nu field, right? So this equation has to be obtained by varying the action with respect to H mu nu field, which means that so before I wrote an action whose variation with respect to H mu nu only gave me this part and this T0 mu nu part. Now if I want an action that reproduce also these two terms, I have to add new terms to this action. So for instance, so how would those new terms look like? Schematically, those new terms are look like H mu nu coupled to T1 mu nu plus T2 mu nu. Although this is very schematic because you really want to write something whose variation with respect to H mu nu reproduce those terms. And since these this one already contains, so this is, remember, it is order h mu nu. It contains one h mu nu in here. And here we have 2 h mu nu. So when we do variation of the action with respect to h mu nu, it's not just coming from this h mu nu. There has to be something more, something different, but when I vary it, reproduces these two terms. So I have to write something that reproduce those terms when I vary the action with respect to h mu nu. But one thing that is clear is that that action, that term, so now since this is too schematic, let's don't write it. So instead I call it, so what do we call them? Let's see. So let me write it as S. I write it as S coupling 2 and then S3, S gravitational 3. So let's give this also a name. So this is S coupling 1 and this is S mat. And this is S gravitational 2. So what is the meaning? So this is the gravitational action which is second order in h mu nu. This is the coupling between the h mu nu and matter field, which is first order in h mu nu. And then here we have the matter action. Now what do we want? What do we need to write to reproduce these two terms? What we need to write is to add a coupling between h mu nu and matter field, which is not second order in h mu nu. So that when we take the variation of this S coupling 2 with respect to h mu nu, that gives me this T mu nu 1. So the action is quadratic in H. When I vary it with respect to H, it gives me a linear term in H, which is this one. And then there has to be this S gravitation 3 so that when I vary the action with respect to H mu nu, it gives me T2 or T mu nu 2. Gives me this stuff. So this is a purely gravitational action, only knows about h mu nu, and it is cubic, so that when I vary with respect to h mu nu, it gives me a quadratic term in the equation motion. So these equations can be solved. One can find this as coupling 2 and its gravitation 3 to reproduce this terms. But the moment we add these terms to the action, then we have again a problem, because now the sum of these three terms by itself is not conserved, because now we have new terms in the action, new interaction, and it's only the total energy momentum tensor of the full action which is conserved. So the full action now contains these two terms. I have to add the stress or energy momentum tensor that I derive from these two. So how would they look like? The one that I derive from this is energy momentum tensor that contains matter fields and 2 h mu nu. So there will be a term here which is T2 mu nu coming from this coupling. And then from this cubic term, for h mu nu, if I apply the Northern procedure, I will get a contribution, purely gravitational contribution that is not cubic in h mu nu. Now I guess we can imagine what is going to happen. Then I'm going to write the action for this that reproduces this term, and the action that reproduces this term, and then I have to derive the energy momentum tensor of those and add them, and then this procedure continues forever. Now the claim is that if you continue it forever, you get the Einstein theory of gravity.
Why did the capital T mu had included the H field inside? If it's coming from matter?
This one?
Yes.
Well, this is the one that I'm deriving from this part of the action.
Because of the interaction,
Yeah.
you can say that the new T mu nu, which is just matter part, or when we say capital T?
Well, at the moment I'm talking about this, I mean, these are just names that I'm giving to, but so these terms correspond to the energy momentum tensor that you derive from various terms in the action, right? So I don't know, you can call them differently, doesn't really matter. But this T1 mu nu is the term that I derive from this coupling, which is linear in h mu nu, but it also contains matter fields. So that's why I called it with the uppercase T, because it contains matter. But it's not a universal convention. You can call it whatever you like. The point is that once I write this action, then the conserved energy momentum tensor of this action would be just unique. One conserved energy momentum tensor and has to know about all three terms, all three parts of the action. So there is T0 coming from here, there will be a T1 coming from here, and then there will be this little T2 coming from there.
In this case, we will have at the quantum field level a theory where you can vary the number of vertices, the gravitational vertices, for example, the H mu nu, but you still have for all those which by continuing the maybe you continue to like to add to include infinite possible of putting the infinite number of vertices to
yes, yeah.
But with the same coupling constant G.
Yes, yeah, there will be some numerical coefficients, but there is no free parameter. Yeah, there you have an infinite set of couplings which are all fixed in terms of just G Newton.
And when you solve, okay. But you, when you, for example, if you consider a scattering, a simple scattering, like let's say 1-1. At that case, in between, you will have, I mean, a very huge amount of
diagrams,
for example,
so
finite diagrams. So you will have an infinite number of amplitudes.
Yes, so but this is the fact that you have an infinite number of diagrams is true even if you have a single interaction, because then you go to various number of loops. So for any process you'll have an infinite number. In any interacting theory, you will have an infinite number of diagrams, which are organized by the loop counting, right? So at any loop order, you will have some number of diagrams, right?
Yeah, but here's different. You
Yeah.
have a loop, like you.
But here is not that different, because so you imagine you are considering this scatter, right, between, so there are two matter fields and they are gravitationally interacting. Then what can you do at tree level? You just exchange a gravity. That's it. If you want to add more gravitons, then you start getting loops, because what do? Either you add another one of these interactions. So this is a loop diagram.
No, but what I mean, you can add at the same vertex of that here,
Yeah.
from here, another graviton.
And then where do I take it? Here?
I think, yes.
But again, it's a loop diagram.
Okay.
But it's true that there is an infinite set of couplings which are all fixed in terms of what we originally wrote. So yeah, this structure is completely fixed. There is no freedom, and therefore, as you go higher and higher order in perturbation theory, you know with what coefficients you have to include this new diagrams. But there is but it doesn't mean that you cannot do perturbation theory to calculate your scattering amplitude. You can do perturbation theory. Meaning that there is an organizing principle here. You can restrict yourself to tree level scattering, and then you will have only one diagram.
But for example, the first coupling with T0 will be vertex kind of two matter fields and one graviton.
Yes.
But if we go to the first order, we will have now at least two gravitons coming out with the...
Yeah, so that was, so from here, here what we would have would be just one graviton coupled to your matter.
Right.
Or this, if this T0 was if this matter interaction was, matter action was interacting, it could be more matter fields connected at the same vertex. So it could in principle include more matter fields, but only one gravity.
Yes, but now is coupling 2, which is second order in H.
Yeah, so now here it looks like this.
So, okay, and then if we go out, greater and greater number of gravitons in the same vertex, but still all three level diagrams with being one order in the coupling constant, first order, we will have infinite such diagrams. Not on. So that's what I think you asked for asking. Even if we do not consider the loop diagrams, we just consider diagrams such with just one vertex. We will have infinite number of vertex with infinite number of gravitons.
Yeah, that's true, but these correspond to different processes.
But even so, we still can work with perturbation theory on those.
Well, yeah, because they correspond to different processes.
Yeah, because
If you wanted to consider, you want to consider matter scattering due to gravitational interaction.
Which couplings we're considering? Okay. Right.
Yeah, so for instance, that coupling would be relevant if you wanted, so this is a 2-to-2 process.
Right.
If you wanted to look at the 3-to-3 process, or 2-to-4 process, then that would contribute to that would lead to a 3-level diagram in the 3-to-3 process or 2-to-4 process. Now that I'm drawing Feynman diagrams, let me also do this for fun. So it is self-interacting. Yes, okay, so yeah, this is a claim. We are not going to verify this claim here. We are going to take another route, which is more efficient, or easier to construct a full nonlinear theory. But at least this shows the fact that the system is very constrained. So there is not arbitrariness here. It's basically the full answer has to be fixed. We just need to find a way to find that final answer, which is the Einstein equation. Okay, so the trick to use, the shortcut is to use, to get inspired from the Maxwell theory. So let's go back into Maxwell theory. There we had a similar situation. We had Maxwell equation, the mu f mu nu equals j nu. And this f mu nu had the property that it was identically conserved. Which meant that j mu has to be conserved on shell. And we know that this fact, the fact that this d mu nu is d mu nu f mu nu, but this left-hand side of the equation is identically conserved, is just a consequence of the fact that when we wanted to construct an action for the A mu field, which describes a massless spin 1 particle, we realize that A mu field has too many components, so we have to impose some extra symmetry, this gauge symmetry, to get rid of those extra components. That gauge symmetry uniquely fixes this left-hand side of the action, which has this property. And then, therefore, this A mu cannot be coupled to any random thing, any random vector. It has to be coupled in a special way. Particularly, it has to be coupled to a conserved current, or more precisely, we have to find a matter action which has a symmetry and an associated conserved current. And if we find such a matter theory, then we can couple these two together. Or we can couple this A mu to the current corresponding to that matter field. How do we do that? What we do is basically the following. If you remember, we said that if we have an action with a symmetry, then we have some transformation, delta psi, and that transformation has some parameters. Then we said that if we promote the parameter of that transformation to be an arbitrary function of space-time, so before that, delta S sub psi would be 0, or would be a total derivative, d mu or something like that. Then we said that if we promote this A to be an arbitrary function of a space-time, then delta of S now is A of x. Of the psi is going to be given by there is d4x here. It's going to be given by d4x, maybe a minus sign, d mu of this parameter A of the transformation times the current. This is another current that we say has to be conserved unshaped. Now, if we have a situation like that, on the other hand, we said that we want to impose a symmetry, a mu going to a mu plus d mu of some alpha. Now, if we had a matter action with some symmetry, with this symmetry, whose symmetry parameter is just a constant, is just a single variable, then we can couple these two systems. We can couple A to psi using the following procedure. The procedure is that I write S of A and psi in such a way that delta, well, I identify this A of x with this parameter of gauge transformation of A mu. And then require that this full action is invariant under this, now we call this a local transformation. Is invariant under this local transformation. So what is this action? Well, part of it is what I wrote before. This minus d4x d mu A j mu, and then there has to be some other part which comes from the variation of whatever Lagrangian coupling that I wrote with respect to A mu times the change of A mu d mu A. So we want these two to cancel, which means that the current has to be the derivative of this interaction. Let's call it the interaction. An interaction with respect to A mu. So if I construct the action in this way, then I have succeeded in making the action invariant under this gauge symmetry. But moreover, what appears now on the right hand side of the equation will be a conserved current. Now, this procedure is usually called gauging the symmetry. So we started from some matter theory, S of psi, with some global symmetry. And then we coupled this psi field to some gauge field, A mu, in such a way that now the action is invariant under the local version of that symmetry.
Is this why we call the gauge freedom in the A mu nu as a U1 symmetry? Because only when we have the interaction, we gauge the U1 symmetry in the fermionic wave functions. Only free photon field has a gauge freedom.
Yeah.
But it has nothing to do actually with U1 symmetry or anything like that. Unless we have a fermion field in the context. Unless we gauge the U1 symmetry that fermions have.
Well, when we say U1, what do we mean by U1? So U1 is a group. So when we say this gauge symmetry is U1, we mean that under composition, it has the same properties as the U1 group. Now, let's forget about the matter field. Just take a mu phi and ask: does the composition of, say, two subsequent gauge transformation, does it satisfy the composition law of the U1 group? And the answer is actually yes. Locally, they have the same property. That if you do a gauge transformation with parameter A1 and then afterwards you do a gauge transformation with parameter A2, then it's equivalent to doing a gauge transformation with parameter A1 plus A2. And now you can identify this A parameter with the now that you have a represent, which means that this A parameter it produces a representation of U1 theory, because you can consider elements of U1 which are e to the I alpha x, and under composition they have the same behavior. It's not very sophisticated, but it is actually the same composition as U1. You might ask about the global property of the group, because when you say U1, you want to come back at the same point after 2 pi. This is something that when I write this, since I'm just writing an infinitesimal transformation and the topology of the space is that I'm considering here is trivial, it wouldn't matter much. But yeah, in principle it can be. I haven't yet defined it in a sense. But you could define it to be U1, which means that if you, for instance, if you have a hole and then you do a gauge transformation, so if you have a loop which goes around the hole and you do a gauge transformation that changes by 2 pi, then you come back to the same point. So this allows you to have non-trivial winding numbers if you are actually U1. So depending on whether I do have these non-trivial winding numbers or not, yes, it might be U1 or not U1. We call it U1, I think, because of the it has the same Lie algebra, so near the identity element it behaves the same as U1, even though globally it might not be, might or might not be like U1. I haven't really said anything about it.
Could I also gauge one other symmetry that matter field has, which is not U1, with this A mu gauge field?
You mean A mu gauge field?
A mu, yes.
No, because we want to identify the parameters of these transformations. So no, they have the same properties under this composition. So they have to be the same group.
If the global symmetry is only one generator, let's say, we can only identify if the gauge transformation is like that, like A mu some scalar function. Okay. But if the general global symmetry has some, like SU2 global symmetry, then we have to choose correctly how would be the gauge transformation.
Yes.
And there's just one choice of how should be the gauge.
Yeah, exactly. It will be the same group. You go from a global symmetry based on that group to a local symmetry. Okay, so this was just for inspiration, and then we do the same thing in the case of gravity. So if you remember, we had this linearized diffeomorphisms as a symmetry of the linearized action or linearized theory or the quadratic action. And then the source that we put here was the T mu nu, the stress energy tensor. So we said that we need a conserved current, and the candidate that we have for this conserved current is the energy momentum tensor, which is the nodal current associated to the space-time translations. So now the analogy is probably clear. We have H alpha beta or H mu nu field, which is supposed to describe a massless spin 2 particle. H mu nu field has too many degrees of freedom, so we need to impose a gauge symmetry, which is this.
Can I ask a question? Because before we proceed, because when we keep added the higher order of H terms, did we consider anything about that those terms are gauge invariant or not? Diffeomorphism gauge invariance or not? We didn't consider if they are dimorphism. We just add all the.
Yeah, there I didn't. So this action that I wrote here was invariant under this linearized diffeomorphism. And then we decided that the only way to get a consistent equation at zeroth order is to write this coupling. Afterwards, I was just following a necessary requirement, which is that if I hit this equation by d mu, it has to vanish. So then my guiding principle here for writing this term was something else, but not totally unrelated. The fact that this is zero, the fact that this the equation of motion for H mu nu, the homogeneous part of the equation, is identically conserved, is a direct consequence of the fact that this quadratic action that I wrote is invariant under that symmetry.
Yes, but I'm talking also about the higher order term. Are they diffeomorphism invariance or not?
Well, until I write the full theory, no. In fact, that's basically the way that we are going to find the full theory. We are going to write a theory that is invariant under this diffeomorphism. Basically following the same rule that we see in the case of Maxwell field coupled to matter field. What we do is that we say the Maxwell field A nu has to satisfy gauge symmetry. Now in this case we have diffeomorphism. In the case of Maxwell we have just the U1. Now we want to couple H mu nu to matter fields in such a way that the full action is invariant under this symmetry. So what source we do, or now the natural question is that what am I going to identify this parameter of a gauge transformation with what symmetry of the matter action is going to be identified with this, and that symmetry is space-time translations. So if you remember, we had this, there was T mu nu was the conserved current associated to the symmetry H mu going to x tilde mu equals h mu minus some constant translation, we said that the symmetry under this transformation will give us T mu nu or T mu nu 0 before adding any gravitational interaction. So what we do now is that we identify this A mu and xi mu and construct a full theory which is invariant under now local versions of this space-time translation. Yes.
But you said that there, but it's fine. That if we proceed with the higher order terms, we will pick up Einstein equations. But but that I think that way of proceeding is it should be completely different than the way to just restrict the gauge and couple the two actions with the gauge invariance term. They are not equivalents, right?
They are. Well, I don't know what you mean by equivalent. They are equivalent in the sense that they give the same answer.
But that one, that one doesn't respect the gauge, and that one respects. So,
yeah, this one at the end of the day, I'm going to construct a full theory that will satisfy the same. My claim is that if you follow this procedure, just without thinking, just keep adding terms in this action. You just follow this procedure without any thinking, at the end you are going to obtain a theory that satisfies, which is invariant under this diffeomorphism. How do I? Well, maybe at the end I can come back and convince you that is the same theory. That in a sense, at the end of the day, imagine I give you some action here. Imagine I give you some action so that when I derive the equation of motion for h mu nu, and when I linearize with respect to h mu nu, then I recover this first term. And then there will be some higher order corrections to this action. Then I have basically achieved the same goal. And that's what we are going to do. We are going to write some action so that when I derive the equation of motion for h mu nu and linearize, I reproduce that. But there is a fully nonlinear equation that is consistent, and that's the only thing that we desired. We only wanted to find a nonlinear compilation of this equation which is consistent, and I'm going to propose one. There are actually papers about this, but once you think about it in this way, it's kind of obvious that the nonlinear compilation is unique. So the moment I give you one candidate, that has to be their solution. Okay, so yes, we want to take some action for this h mu nu and matter field. With the requirement that now it is invariant under local diffeomorphisms, or local translations. So before we just considered normal translations which are global, and that would give me conservation of currents. Now we want to promote this symmetry to a local symmetry and construct the action that is invariant under that. So now what we can break this task into two parts. We can divide this action into a gravitational action plus a matter action. Now it's a different matter action because there will be, I'm also including h mu and nu in here. So this decomposition is well defined. I can pick, I can always separate the action into terms that do not contain matter fields at all and the ones that do contain matter fields. So there is this is an unambiguous decomposition of the action. And now we want to ask, at least in this section, we want to ask, what would be this matter part of the action? Let's first focus on the matter part and see how we would construct the matter action that is invariant on the local coordinate, local translation. So these transformations have various names. Diffeomorphisms, for instance. The other name is well, the resulting theory is also called generally covariant, or just simply coordinate transformations, general coordinate transformations. So we want to construct a matter action with that property.
How can we see that it's a coordinate transformation?
How?
Can we see that this is actually a coordinate transformation?
Well, it is.
I mean, like in tensorial language, it would be del x tilde mu over del x alpha times x mu gives us x tilde mu, something like that. Like tensorial transformation of the coordinates. That's what
I'm not sure if I understand.
Linear transformation?
like one coordinate which transforms one coordinate vector which transforms as a tensor. So that tensor transformation, that matrix, is the coordinate transformation there, right?
Are you talking about this object?
Yes. Yes.
Yeah, so this is a general matrix. That would be our coordinate transformation.
So how can we connect with this parameter with that kind of a transformation?
Well, in the following way, we are just considering small parameters here. That's enough. I mean, you don't have to, but for all of our purposes, it's enough to focus on the small parameters, and then this transformation becomes just delta mu nu plus d nu of xi mu. So this is your transformation matrix. However, we are talking about fields that are functions of coordinates. So the transformation laws would be the things that you are familiar with. We use the transformation laws are the ones that we use to go between various coordinate systems. So if I have phi of x, if it is a scalar, it is equal to phi tilde of x tilde. And then if I have a vector, it will be equal to dx tilde, or this is called a covariant vector, will be dx mu a mu of x tilde, and then so on. So yeah, so we want to construct a theory for various fields, so these are, for instance, our matter fields. The theory that so that the action is going to be invariant if I apply these transformations to the fields that we have. So now we have to, there are various steps. There is a prescription to construct such an action, which is what we are going to consider now. So let's first remember, when we were talking about Lorentz invariant actions, we would take derivatives or vector fields or tensor fields and would construct, using them we would construct a Lagrangian, which was a scalar quantity. How did we construct that? We used the metric, the Minkowski metric, to counteract those Lorentz indices, and that ensured that this is the scalar quantity on the Lorentz transformation. Now, so for instance, we would write, in fact we even wrote it today without writing the indices explicitly. We would write some Lagrangian which would look like this: d4x eta mu nu d mu psi d nu psi, and that was a good action for on the Lorentz transformation. It was an integral over a space-time of a Lorentz scale. Now this is no longer a valid action if I want to require general coordinate transformation or symmetry on the general coordinate transformation, simply because this eta mu nu is not invariant on the general transformation. So if I multiply this eta mu nu by those transformation matrices, remember that eta mu nu is just a set of numbers. It's a matrix, a fixed matrix. It's not a field or anything. So what does it do? If I multiply by dx tilde mu, dx delta dx tilde nu, that is not equal to eta alpha beta. Since it is not equal to that, this action will not be invariant on the general transformation line. So what is the task? The task is to use the fact that we have this h mu nu, which also transforms, and it transforms in a non-trivial way. It does not transform like a tensor on the coordinate transformation. In particular, there is this extra terms which are nonlinear in h mu nu. They survive even if I set h mu nu to 0. That makes it obvious that it's not a tensor, because if you have a tensor, if it vanishes in one coordinate system, it has to vanish in all other ones. The fact that I can start from 0 and make it non-zero, it means that it is not a tensor. Yes?
This is like the polarization vectors of the A field. It does not transform as Lorentz, the transverse at least, the transverse modes. It does not transform as Lorentz vector, but some vector plus some vector along the movement of.
Yeah, this is the same thing. This is the consequence of the same redundancy at the level of polarization vector. Now remember, this h mu nu field, we want to write. We would write it in terms of some linear combination or creation and annihilation operators for actual gravitons, and then we had to multiply them by some polarization vectors. The fact that this corresponds to the fact that those polarization vectors are not uniquely fixed; they have to be identified with up to some transformation. Okay. So what is the answer? I just write the answer. If I construct the metric G mu nu, which is eta mu nu plus H mu nu, we can see that then it is invariant. No, well, not that under this, but now G mu nu maybe I lower the indices. Yeah. Here this is at point x, this is at point xt. Well, you can verify this equation. Say if h is small, I can verify this equation at, say, 0th order in H mu nu. And then at higher orders, there will be the question of how this H mu nu field transform, because I haven't said how this H mu nu transform at higher orders in H mu nu. In principle, there is some more complicated transformation law here. It's more or less a matter of definition, how I define this H mu nu field. Only thing that is fixed for us is this part of the transformation. The rest is so far not fixed. So in particular, we can fix it by saying that, or the metric that is defined like that satisfies this equation to all orders. That can be thought of as a nonlinear fixing of the transformation law of H mu nu.
We are abstracting the tensor
Yeah.
through just matrix with numbers eta, something that transforms weirdly, and their sum is transforming literally like a tensor.
Yeah.
At least in the linearized order, we know that.
Yeah, at linearized order it does that. At nonlinear order, the transformation of H mu nu has not been fixed yet, so we basically fixed it by this requirement. You didn't have to do it, but this is the easiest choice. And other choices are just related to this one by some simple field redefinition. So then the rule is very easy, or at least the first rule is very easy. The first rule is just to, wherever we have eta mu nu, replace it with G mu nu. And similarly, if I have eta mu nu with upper indices, I replace it with G mu nu with upper indices, which is defined as the inverse of G mu nu with lower indices. So we define the inverse metric G mu nu, which has the following property: G mu nu G rho nu is equal to delta mu rho. So the upper index G mu nu is just defined as the inverse of the lower index G mu nu. So I should say that these are, if you have had some mathematical physics course in which they talked about curvilinear coordinates, like spherical coordinates and stuff, I'm not doing anything extraordinary here. If you wanted to have a description or a system on curved coordinates, you would go through the same procedures. Okay, so this is the first step. The second one is that, oh, by the way, this should also look familiar from the point of view of point particle action. If you remember, we had a coupling of point particle action to H mu nu, and we showed that at least at linearized order, it's equivalent to replacing eta mu nu with this g mu nu. Okay, so now the second step is to take care of derivative. So this is very similar to what happens in, say, U1 gauge theory, in Maxwell theory, when we couple it to the charge field. If you remember, when we have a theory for the charge field which is invariant under global transformations. Once we make the transformation local, then the derivatives have to be taken care of with more extra gauge field. Why? Because now the derivatives can act on the transformation matrices. So, for instance, if I have a field theory which has a U1 symmetry, so this phi is a complex field, and this is invariant under phi going to e to the I a phi, where a is a constant. Now, if I want it to be invariant under a transformation when this a is not constant but a function of the space-time, then I have to change these derivatives, because now the mu phi goes into e to the I a of x times the mu phi, well, let me factor it out, the mu plus I the mu of a times phi. And then, therefore, this kinetic term is not invariant on the local transformation. In order to make it invariant, what we do is that we define the covariant derivative, the mu of phi, which is the mu minus I a mu of phi. And then if we take into account the fact that a mu field itself transforms under this symmetry, and we have identified the parameters of the transformation, then the mu of phi, the covariant derivative of phi, does indeed transform in a simple way. And therefore, if I write the covariant derivative of phi norm squared, then that would be invariant. So there is a similar story here. If I have derivatives of derivatives of vector fields, then under coordinate transformation, they are not. So derivative of vector fields in the case of when we just talk about Lorentz, the derivative of a Lorentz vector is a Lorentz tensor, for instance, right? Now it's no longer the case, because if I consider the mu of a nu, then under the transformation, so how does it look? We want to write the mu of a nu, but now with the tilde. This is the mu tilde. This is a mu tilde. Now this is equal to dx alpha dx tilde mu d d by d x alpha times d x beta dx tilde mu a of beta. I'm dropping the arguments, but you should remember here is a function x tilde. Here is a function x. Okay, now we see what happens. What happens is that now this object is not going to be, so there will be a piece which transformed the way we expected it to do. But then there will be the extra term that comes from acting by derivative on this transformation matrix itself. So that would be so that's what that is, a dx alpha dx tilde mu d2 d2x beta dx alpha dx tilde mu. So let me write it in a more reasonable way. I guess the most reasonable way is to just write it as d2x beta times dx tilde mu dx tilde mu times a beta. So there is this extra term, or this extra term. If it was just the first term, it would be the transformation of the tensor, but now there is this extra piece. It's very similar to this extra piece that we have here. Before, when we were talking about if this was a Lorentz transformation, then it would be just a constant matrix, and then its derivative would vanish. So this term wouldn't be there if we were just talking about Lorentz transformation. But now when we consider general coordinate transformation, then this will be non-zero. It's very similar to the appearance of this term here. And the resolution is also very similar. We just construct the covariant derivative by adding some extra terms which depend on our gauge field. Now our gauge field, maybe a mu wasn't the best name to choose here. Now our gauge field is h mu nu. So we construct this covariant derivative by adding something that depends on derivatives of h mu nu, which is this, which we call them Christoffel symbols. And what they do is that these Christoffel symbols, they do not transform like a tensor, but the deviations from transforming like a tensor exactly cancels the deviations of this object from being a tensor. And what are they? They are just constructed from h mu nu, which is now put inside this matrix G mu nu. So you have some expression. Gamma alpha mu nu is given by G alpha beta over 2 d mu G mu beta plus d mu G mu beta minus d beta g mu. Now we can one can check explicitly that this object does not transform like a tensor. And its its deviation from being a tensor is exactly like that. So that term would cancel this term.
For the G, we choose that rule that it transforms like a tensor. For G, it transforms like a tensor.
Yeah, G does transform like a tensor, but as we saw, the derivatives of the tensor, the normal derivatives of the tensor do not transform.
Oh, okay, the normal derivative.
Yeah, so these are just normal derivatives of G mu nu, and therefore they don't transform. Now this covariant derivative, you should write it like this, just to be consistent with it. That way. This covariant derivative, by the way, you can see that there are some objects for which this mismatch doesn't matter. For instance, as you see, this term is symmetric under the exchange of mu and nu. So if I construct the antisymmetric field strength, d mu a nu minus d nu a mu, that object is a tensor, even if I use ordinary derivatives, because that extra piece cancels from the transformation of two terms. This has some deeper reason. It's because if you think about thinking the language of differential forms, this f mu nu is a second differential form that you construct using the exterior derivative, and that is a well-defined way of constructing tensors. So you don't need a connection, a Christoffel symbol like this to define this. But we will see it later. Okay. You don't need to worry about it.
So the aim will be to write an object which is function of h or g maybe that transforms nicely and like a tensor, even though if we use normal derivatives.
Yes. Yeah, so now this combination does transform like a normal rank 2 tensor. And now we can use this, for instance, to construct diff invariant Lagrangian density. So for instance, we can square this.
So now if in the original Lagrangian we wrote for the h, we just replace all the derivatives by covariant derivatives, then the work is done or not?
Oh well, at the moment we are focusing on the matter action.
Okay.
So in the matter action, you could in principle imagine that you have matter fields which are vectors, vector field, and then right. So we are trying to construct a matter action which is invariant under this diffeomorphism. Now this psi could be some general, some vector or tensor field. So I guess we are done. This could be a vector tensor field, and the rule is that if we have derivatives of that, it should be all derivatives have to be replaced by covariant derivative. now you see that, for instance, the covariant derivative of a scalar field is just a normal derivative, because so the general rule is that for a rank n tensor field, we need n of these Christoffel symbols. So the scalar field is like a rank 0 tensor field. It needs zeros of this. For higher tensor fields, we need more of it. So that's the second rule. The mu goes to nabla mu. And then there will be the third rule that we'll discuss on Friday. And we'll continue.
And now in the point particle action that we have replaced H by, eta by G.
Yeah.
And now the equation of motion for the point particle will change also, because now it wouldn't be a straight line, because it's not flat space anymore. We now have some.
Yeah, but that change, we already saw that it changes even at linear order.
Okay.
The only thing is that now we don't want to linearize anymore. We want to calculate the full equation at all order, which is valid at all order in H mu.
That's the geodesic equation, right?
Yeah. Yeah.
These are all consequences of gauging the translational invariance according to the gauge freedom that H mu has. Right?
Mm-hmm. Yeah.
All these follow from there, and they are somehow coincides with the curved space-time metric and all that kind of interpretation too.
Yeah.
These are two different kind of ways to reach at the same.
Yeah. This is more, but this would be the direction from particle physics point of view. You identify your degrees of freedom and interactions and construct the Lagrangian or the action.
This what we did here is that we start with the simplest matter field, which is the scalar, to try to find general coordinate transformation for it, and then we found that we need to introduce some other vector field mu, which is matter field, and then we start to find the transformation for this new vector field. Is this the
no, sorry.
This
was the bad choice. This was my bad choice of variable.
I see.
So this story is just to give you just an analogy.
Yes.
This A mu has nothing to do with this A mu. You can call it something as V.
So we didn't start to discuss the scalar matter field with to couple to some general transformation for the scalar.
Well, for the scalar, we had some discussion here. This was the action, the kinetic term that you would write for a scalar field.
You rule it out.
Say it again.
We rule it out.
Well, no, we just said that we have to replace eta mu nu with G mu nu.
And we done. We will be done.
And then we are done. Except for the third step that I haven't talked about. But
so there will not be a what the transformation that we will do for the scalar matter field.
Well, the scalar field it is just psi of x goes to psi tilde of x tilde. That's just by definition of being a scalar. The field at the new coordinates is just the same as the field in the old coordinates.
So in the light of this transformation, we cannot. Okay. Yes. But we will have the ordinary derivatives for them, not the covariant derivative.
Yeah, so this is okay. This action, if I make this replacement of eta with g, it becomes, well, if you just look at this Lagrangian, if you replace this with g mu nu, this Lagrangian is a scalar. It's a scalar quantity, so it's good enough. There is a problem if I have vectors or tensors and I'm taking derivatives of those.
Yes.
And that's what we discussed there. You have to replace the. In principle, you can also change these derivatives with covariant derivative, but it doesn't make any difference. So in order to be uniform, we can just replace all ordinary derivatives with covariant derivatives, which was defined there. Except that covariant derivative depends on what it acts on. If it acts on a vector, there will be this. But the covariant derivative of a scalar field psi, for instance, if this psi is a scalar field, the covariant derivative is just the ordinary derivative. Or in other words, if psi is a scalar field, then the ordinary derivative of psi acts like a vector field. There is no extra thing that you need to cancel.